Hello, I'm Eugen Hruska, and I want to talk about some datasets for chemistry, from chemistry, and talking about the ground truth explanation. So this work was done as a postdoc at Emory University in Georgia, and this work was done in Fang Liu's lab in collaboration. I will talk about the collaboration later. So the idea for this paper, the preprint, came as part of a collaboration with computer science, where the size of these data sets, the limited size of these data sets was noted. So I came up with an approach how to generate, from a chemistry standpoint, larger data sets. And I will introduce the general approach and also some results from analyzing this data set. Should I continue? All right. So why are the data sets in ground truth chemistry explanations limited? So I will start first. I will assume that everyone has some general understanding what machine learning explanation generally is, but I want to introduce also what the chemistry approach to explanations are. So for example, here we see a small molecular graph, which is widely very simple chemical molecule. It's a stable molecule. It's a simple acid. In fact, acetic acid. So it has some property. Now we want to ask what causes this property. And since it's a simple molecule, we know that the four atoms on the right side are responsible for that, and everything what's on the left side of that is not relevant to this property. So we could set this very exact and precise explanation for this particle molecule. Of course, it's not always precise, but when we compare that with chemistry, with the machine learning approach, where we can just remove a node, in this case, an atom, and see what will happen. So if we remove a whole node in a molecular graph, we will get a radical, a very unstable, and in most use cases, not a really useful molecule. And it will react further, so it's not something where you will have a property which you can use. So this machine learning approach, where we remove or just remove a whole node, is in chemistry terms not necessarily valid, and would be more like alchemy than a chemically valid procedure. So for that reason, having a chemical validity is quite important if talking about ground truth chemistry explanations. In fact, there are already a long history of different explanations in chemistry. One of the more widely known is the Hammett equation. The Hammett equation was formed in 1937, so quite a while long. And here you see the R, the red R. The explanation is like, how does a certain chemical property, some kind of reaction, the reaction rate constant for that reaction, how does it depend on the functional groups here noted as R? And on the left side of R, that part, the ring stays constant, and only the R itself is changed. It can be just one atom, like the hydrogen, or two atoms, OH, or three atoms, or four atoms. And generally, it's just a functional group, and we just replace it and see what the experimental value for this chemical property is, and that would be the Hammett equation. And it turns out that you can do a linear regression here and explain in that sense chemistry. In general, this doesn't have to be a change of just a functional group, but it can be just a change of any kind of subgraph. It can this is called moieties, and as shown in this example, you replace a ring in the middle of the molecule with a ring with a different kind of ring in the middle of the molecule. But the common part here is that both molecules before and after the change are chemically valid, and there is no radicals or just partially removed atoms or something. So there's this chemical validity as a property which defines, it's central to chemistry-driven explanations. So I just showed two examples, the Hammett equation and the general moieties, but there is a long history of chemistry-driven explanations, which basically last as long as the chemistry lasts around the century, where we have different approaches, first linear, then non-linear, and more data sets, just in parallel with the more machine learning approach, where explainable systems is in 1977, and the term XAI is around 2 decades ago was started to be used. So this historical comparison is just to show that this kind of chemistry-driven explanation has a long tradition and is almost independent from the machine learning explanation approach. But in the recent time, there's a lot of overlap. So I want to show also another example, more machine learning driven, which is the counterfactuals. Counterfactuals is minimal difference of the property, and maximal property difference, and minimal difference in the molecule. And when applied to chemistry, to the same molecule I shown as an example before, we see that for the acid, where the 4 atoms on the right side of the molecule are necessary for the acid property, the counterfactual might miss some of these atoms. So that's one of the drawbacks of counterfactuals, that you might not miss all the necessary part of the molecule which define your property. In general, this is just an example of how different explanations can vary, and it's also not always unique. So to summarize this kind of comparison between chemistry-driven and machine learning-driven, the chemistry explains more the chemistry, and the machine learning explains more that particle trained with the machine learning model. And chemistry can have a ground truth explanation in a specific domain. And in machine learning, there could be different explanations which can be valid depending on what kind of parts and representation you're interested in. The chemistry typically uses functional groups or subgraphs, not always, but typically. But chemical validity is always important. For machine learning, this kind of chemical validity is either absent or not necessarily important. And machine learning is many times, not always, has one value for each atom. So taking this comparison was my starting point to generate a larger data set to see how to combine these two different approaches, make them useful for both sides. So it's well known that when calculating explanations for molecules, there is qualitative agreement, but also some disagreement between different methods and more between the more chemical and the machine learning approaches. One example, just very typical here, is where the green and red parts show different explanation values. And we see that in this preprint, there is similarity that the two rings have higher explanation values, but there's also some quantitative differences, but it's not always clear which is the correct explanation. In fact, there are different studies looking both for the more chemical driven, which is the QSAR, and more the graph neural network driven explanations, where different kind of approaches are compared for different kind of data sets. And it's not always, there is qualitative agreement, but also disagreement. And some papers is termed disagreement problem. So from this starting point, I want to continue and figure out why there are these different results. So here's the schema where we have the different losses when we calculate explanations. So on the top part is just a typical, as input are the molecules, output is the predicted property. We have the first loss, which is the accuracy in predicting the property. But as the second output of the machine learning model is the predicted explanation. And we have a second loss, which is the accuracy of the explanation itself. If we have a ground truth explanation available, we can calculate the difference between the predicted and ground truth explanation, and that's accuracy. But there's also other metrics where we can compare either the explanation between different models or the stability when making small changes, which is generally the reliability of the explanation prediction. And all these, the loss of the property prediction, loss of accuracy prediction, loss of explanation prediction, and reliability are different metrics which might be relevant in different applications. So this is one of the reasons why different explanations might be valid at the same point, because the different metrics might be more or less important. For example, sparsity is one of the metrics, since one might want to have a more sparse explanation than in other applications. When we look only at the ground truth explanations, the limiting factor there is the size of these ground data sets. Here I've shown some of the more widely used ground truth data sets for explanations applying to molecules. And okay, let me just walk through the explanation. The first two are explanation data sets for simple property. Is there a ring of different size present or not? These rings are relevant to chemistry, but they are quite simple properties. It's just a ring. So it's not necessarily a complex chemical property. The third and fourth data sets are the presence of the different functional groups. So in essence, just handcrafted subgraphs for certain mutagenicity or liver toxicity properties. The drawback here is that the number of data points is limited because the number of subgraphs is limited. Also, there's no long distance dependency. So these subgraphs are small, so there will be never long distance dependency for these explanations. And the last two data sets are counterfactuals. And as I discussed already before, counterfactuals might miss some essential parts of the explanations. So these are just some examples of the data sets, but they have in common that they are either limited number of data points, less than the order of thousands of molecules, or the chemical properties are trivial and typical also there is no long distance dependencies. So the goal in my work was to generate larger data sets for chemical explanations which do not cover don't cover trivial properties. So when looking at the comparison between the chemistry and machine learning model, I prioritize these parts. The part on that this is a ground truth, and also that every step has to be chemically valid. I would not allow any alchemical steps, which in between, but also in difference to the chemistry approach, get exactly one value for each atom. In chemistry, frequently there is one value for a whole subgraph or functional group, and here I am specifically always give one value for each atom or node edge. So the approach I picked is very similar to the previous one, where we have a pair of molecules and they only differ in a small part of the molecule. And so as an example here, I picked the sulfur atom, the node numbered here 10, and change it in a way that a change will be attributed to exactly one atom. So I picked a decision tree to independently of what kind of atom it is, to have the paired molecule. This is somewhat different to the approach where, for example, the dummy approach where the whole the atoms are either removed totally, because if the atom is removed, it will result in an unstable molecule, or if the atom is replaced with a rarely occurring atom like chlorine or sodium, then these molecules are not necessarily stable, and the property there might not be well defined. Instead, I replace it with commonly, I change it in a commonly common way. For example, the sulfur can be replaced with carbon, but also note that I use implicit hydrogen representation. So the graph is not representing any hydrogens, because the hydrogen can be added later on just by applying chemical validity rules. It's a widely used representation in chemistry and is sufficient in this term. So instead of having every atom as a node, here we have every non-hydrogen atom as a node in the molecular graph. So if there is no non-carbon, if we don't apply or change to the non-carbon atoms in the decision tree, I will remove the node if the node is a terminal node. But sometimes there's also no operation. So sometimes there's no paired molecule, and you might not be able to give an explanation. For example, in the middle of the molecule, you cannot just remove this node and have a chemically valid molecule as a paired. So now we have a pair of molecules, and very similar to the previous approach, we have a pair of property values, and the difference of these property values for these paired molecules will give us the explanation. And this only applies to and this can be attributed to the specific node we will change where we applied decision tree. So in this example, to the index 10, where the sulfur was and was replaced with carbon, and we'll give one number as at the bottom shown as equation, just the difference between the properties. This approach also ensures chemical validity, because if we cannot calculate the property of the molecule, that means the molecule might not be chemically valid. So this is a second guarantee that we have chemically valid pairs of molecule, and we don't use any alchemy. And in this case also, I don't use any radicals and we prevent any breaking of the molecule. So if we break the molecules, so going by causing by the change from going from one graph into two graphs, that would also be an invalid chemical operation. Interesting part of here, what I found is that the property and the attribution value has a unit. So here I was looking at the homo-mono gap, a typical representative chemical property, but its units are electron volts. And the attribution has also these units because it's just a difference between the properties for these two paired molecules. Of course, if you apply this general approach to different properties, you might have different units. In many papers, I have found that the explanation or attribution values don't have any units. And when talking with chemists, they were like, what does this explanation represent? And here, at least, you can say that it's just a difference of the properties when they're changing this particle atom, giving it more chemical meaning.
Hey, Eugene, I have a question.
Absolutely.
Yeah, quick question. So have you heard of the SMILES embedding or kind of format of writing molecules? Because when I read papers about explanations and it talks about chemistry, I usually see that. Is there an advantage of using that one if you're familiar with it?
It's a one-to-one matching between this kind of molecule and a SMILE. The SMILE is just a string representation. So both are chemically the same. Okay. It's just a format which you might prefer. So chemists typically draw molecules as this kind of a 2D representation. The SMILE itself is harder to read for humans. So if you have a chemistry paper, it's easier to explain to a chemist like 3D representation. The string itself is more easier to, I guess, understand for molecule for computer in certain situations. The additional issue with SMILES is that it's atoms which are neighboring. Nodes which are neighboring might not be neighboring in the SMILE, and so like that. Even here, where I indexed the atoms, atom number 0 and atom number 7 are neighbors, and similar in the SMILE, they might be neighboring in the graph, but not neighboring in the SMILE. So that's an issue which I find, but technically they represent the same thing.
Okay. Yeah. Cool, thank you.
There is a actually interesting similarity that SMILES have implicit hydrogen representation. So just like here, the hydrogens are just added on top based on chemical validity rules. And if you want to represent the hydrogens explicitly, you have to explicitly add them to this graph. So there's this similarity for the same reason. All right, so here I've shown the decision tree and the approach for calculating this ground truth explanation values for nodes. But you might note that this is not the whole chemistry, because we have some edges which are different. We have double bonds, triple bonds, and for that we need a bond-wise explanation. So here I picked a different molecule which has a double bond between a carbon and oxygen atom, and we can the same way do an explanation for a disk bond. We can replace it with a single bond and see what kind of explanation we have. Note, in this explanation, I don't use any coordinates, no x, y, z positions or distances or anything. It's very similar to the smallest string, where just the connectivity of the atoms defines which kind of molecule we are looking at, but the bonds are necessary for the explanation of the chemistry. So if you only look at the atom-wise explanations, it might miss some part of the chemistry explanation. And for that reason, I included the bond-wise explanation. Of course, if you, as a benchmark, you might only want to predict the atom-wise or the node-wise explanations, but together, both of them are necessary for this chemistry explanation. So for the bonds, the decision tree is similar, but not identical. Here, we also replace any kind of not saturated bond, so double or triple bond, and we replace it with a saturated bond, a single bond, as shown in the example, and we get the paired molecule. The decision tree is also that if the bond is not saturated, but is part of the ring, you can still remove the whole bond, break the bond, and the resulting molecule is still a valid molecule because the ring still keeps the molecule intact. But in some cases, if it's not part of the ring, it can chemical operations because it will break the molecule into two parts. And just like before, we match these paired molecules in the database, find the property values, take the difference, and for this particle bond, we get the attribution value of just the difference of the properties. And we can repeat that for every single bond. And that's shown in the bottom right in the schematic. Note again, not every bond will give you a value, because in some cases there's no chemically valid match. So I done that for larger data set, the PCQM4M version 2. For the homonormal gap, but this is a general approach. So you could use that approach for any kind of property, either simulated or experimental, for any kind of data set. As long as you have a molecule and a property pair, and you can find these kind of paired molecules in the database, or even generate or even simulate new molecules when you have the paired molecule. So the data set is stored as two CSV files. Each is a molecule index, the operation index for that particle PCQM from version 2. I took advantage that this already existing data set, so I didn't have to calculate all these chemical properties. I just extracted with this general approach, which was quite fast, just simple on the computer. And for each row, I specify which atom or bond this kind of operation in the last slides which I applied to, and which of the molecules is the paired molecule. So the column 1 and column 4 is the molecule and the paired molecule index, and the last column is the explanation value. So with this approach, I got like 3.5 million atom-wise data points and 1.5 million bond-wise data points. These are separated just in case one wants to predict just atom-wise and bond-wise explanations. It's not a large data set, just 160 megabytes available on Figshare. So it's a general license. So here's the generation of the dataset finished. In the next slides, I want to discuss how some of the results I got when analyzing this dataset. So this dataset is somewhat sparse. So not every atom or bond in the molecule will have a value for two reasons. Either this chemical validative pairing got no result, or the paired molecule was not in the first data set. So it did not simulate any new molecules. So if you want to simulate more molecules, the resulting explanation data set might be less sparse. But on average, I got around 2 values per molecule. But there are some molecules which have 5 or more explanation values for a single molecule. I looked at the correlation between the dependency between the chemical property, the homologal gap, and the explanation value itself. And it's quite, there's a very horizontal line, which indicates that the explanation itself does not strongly depend on the chemical property, but for each chemical property, it could be positive, negative, or just around 0. From the chemistry aspect, I found it interesting to look at different node types. So for each different type of atom, like boron, or carbon, nitrogen, I looked at the different histograms of these attribution values, and it's immediately visible that the different atoms behave very differently. The carbon is the most close to 0. It's almost a very, it's a peak shape distribution, but others like boron is more Gaussian shape distribution. And other atoms like phosphorus have a very long tail, which go towards negative attribution values. This can be explained that there are different oxidation numbers of different environments for these atoms. And so it's a non-trivial distribution. For some of the atoms, we have also less molecules, like germanium or arsenic. So there's a significant difference for the different atom types. I also investigated the long-distance dependency or the smoothness between neighboring atoms or neighboring nodes in this molecular graph. There's some papers which assume that the explanation itself is smooth, that neighboring atoms have a more similar explanation and use that as a regularization for the training of explanation. So to check this, I analyzed this ground truth explanation with the topological autocovariance. The topological autocovariance is similar to the autocovariance, just in the space of distance of bonds. So if we have two nodes in a graph at a certain distance, we can calculate the autocovariance depending on the bond distance, the topological distance. So it's a conditional expectation on this distance. And this topological autocovariance decreases, but even at a distance of 1, we have some covariance and only decrease further with increasing distance, which means there is some kind of a similarity between neighboring atoms. And as expected, the similarity decreased with increasing distance. If we just look at the absolute difference of the explanation value, then we have a slightly unexpected. The difference is higher for a distance of 1 bond and for 2 bond. And this can be explained by the distribution of the molecules. There are a lot of metal groups, which is just a carbon atom with 3 hydrogens. And if we have 2 metal groups neighboring, then these metal groups are symmetric and can, due to the symmetry, they have the same explanation value. And which gives, if you take the histogram of that, will give a smaller absolute difference between atoms at the distance 2 than at distance 1, because at the distance 2, you have 2 metal groups neighboring. So slightly unexpected, but also can be explained by the peculiarity of the chemical, the molecules. The same analysis can be done for bond-wise explanation values. Here we don't have any unexpected steps for the absolute difference of depending on the topological distance, and the topological autocovariance also is not zero at small topological distance, which means there is some kind of smoothness. But we also see that even at significant distance, more than 9 bonds, we still see some kind of covariance, which is matches the understanding that this kind of property, the homonormal gap, has a long distance dependency. So changing a part of molecule at one side can change the homonormal gap for the whole molecule, even if the molecule is large, can be larger than 10 bonds. So this is to be expected and potentially interesting to see if machine learning algorithms can predict these kind of long distance dependencies of the explanations, which is different to the trivial data sets of ground-truth explanations for simple properties like the ring, where there's no long distance dependency. Also look at the ring dependency. Depending on the size of the ring, the average value changes with the size of the ring, but also is different than from bonds which have which are not part of the ring. So I highlighted the small ring size of 3 bonds and a large ring with 11 bonds, and there's a smooth change, and the large change between the small rings and no rings is caused by the different the decision tree for the pairing of the molecules, because a ring can be broken, the bond in the ring can be broken, but bond not in the ring cannot be broken to get the chemically valid molecules. Yeah. So as a conclusion, I want to just highlight that this data set is somewhat bridging the chemistry-driven explanations and the machine learning-driven explanations. And with this bridging, it could generate a larger data set, which is available on preprint and on Figshare. This result was as a collaboration with Liang Xiao in chemistry department at Emory University and Pang Liu and chemistry department. Thank you.